Hello everyone. In our earlier video, we got introduced ourselves to trigonometry. We just concluded on this note that there are triangles everywhere. It is left to us to watch these triangles. We'll have to train our eyes to visualize these triangles. Now here, let's consider this right triangle. Let's say this right triangle. It is right angled here. If I call this triangle as A, B, C, it's right angled at B. And let me say that this angle is maybe 30 degrees. And I'm extending the arms of this triangle here, and the base of the triangle also extended. I'm just doing it so that I can draw some parallel lines parallel to BC. So this is my first parallel line, okay, and my second parallel line, third parallel line. I'm just drawing parallel lines. Let me call it also, name these lines. Let me call the first line as TR, the second line as IG, and the third line ON, right? So I have drawn three lines. One is TR, line IG, and line ON. And now just observe these triangles which are made. How many triangles are made? The first triangle, of course, we talked about triangle ABC, right angled at B. What is the next triangle? It's triangle ATR. Triangle ATR. This is right angled at T, right? So if you observe ABC and ATR, angle A is common to both, and angle B and T are right angles. So two corresponding angles are equal. Now let's also include the other triangle, triangle AIG. Once again, A is common, and it's right angled at I. So once again, two of its angles, corresponding angles, are equal in all these three triangles, and also triangle AON. I can say the same thing about this triangle also. So what is our conclusion? By the AA similarity postulate, which we just saw in our past few videos on similarity, all these triangles are similar. Triangle ABC is similar to triangle ATR, is similar to triangle AIG, and is similar to triangle AON because two of its angles are equal. And just to state, if two of its angles are equal, the third angle is also going to be equal because the sum of the angles in any triangle is equal to 180 degrees. So, and of course, one is already a right angle. So we can guess the measure of this angle, isn't it? Because these two have to add up to 90. 30 and this angle has to add up to 90. We can very well guess the measure of this angle, whatever it is. All of them are equal. All three corresponding angles are equal. So the triangles are similar. And once the triangles are similar, we can say that the corresponding ratios also are equal to one another, of the sides. I mean, the ratios of sides, corresponding side ratio. So for example, if I talk about the side AB by AC, this ratio would be equal to AT by AR, right? I'm just writing corresponding sides here. Would be equal to AI by AG. I hope I have written it in order. Yeah, AB, AC, AT, AR. Yeah, I have written it in order, and so on. These ratios are equal because the triangles are similar. Now let me recreate these triangles here neatly. Let me draw three right triangles of different sizes, but which are similar. So this is one, and I can copy it, isn't it? Yeah. So this is another one, and just size bigger. And once again, if I one more bigger than that. So these are three triangles. All of them, what do they have in common? Right triangles, right angle triangles, 90 degrees. And let's also say that this angle is 30. All these angles are 30 degrees. So now all the three triangles are similar to one another because two of its corresponding angles are equal. So I have assumed that this is 30. So this is also 30. This is also 30. So what do we know about the corresponding sides? Now let me take two sides, ratio of any two sides. So the side which is very popular in right angle triangles is the hypotenuse, isn't it? What is the hypotenuse? It is the side which is opposite to the largest angle of a triangle. Of a right angle triangle. What is the largest angle of a right angle triangle? 90 degrees. Because the other two angles have to sum up to 90 degrees. So this 90 degree would be the largest angle in any right angle triangle. And the side opposite to 90 degree would be the largest side. If you compare all the three sides, hypotenuse will be the longest. I should have used the word longest actually, because we are talking about lengths. So hypotenuse is the longest side. So let's take the hypotenuse as let's involve the hypotenuse in our ratio. And now the next side, let me consider this side, the side which is now opposite to 30 degrees. I am talking with the perspective of angle 30, the 30 degree angle. This is my opposite side, right? This is opposite. So if I name this triangle, I've already named it as ABC. Let me name this as DEF, and let me name my third triangle as TRI. Okay. So the corresponding sides have to be equal, isn't it? The ratios of the corresponding sides have to be equal. So let me take the opposite by hypotenuse of the first triangle. If you want me to name them, it is BC by AC. This would be equal to the opposite by hypotenuse of the second triangle, which is EF by FD, which is equal to RI, the opposite to 30 degrees. I am talking opposite to the 30 degree angle which we have considered now. So opposite. So RI by TI. All of them are equal, right? So if you take any similar triangles, I am talking about 90 degree right angle triangles. You consider any 90 degree angle with one of its angles known. That is, if this is not mentioned, then it's different. The ratios may be different. But now since I have mentioned that it is 30 degrees in all the three triangles, all these three ratios would be equal. It would be equal to some constant, isn't it? Which would be the scaling factor, of course. You'll have to go and look at our similar triangle video series if you want to understand this. But here I hope it's very clear now. These ratios, opposite by hypotenuse of all these similar triangles, will be equal to some constant. So whatever triangle you consider, however big you can imagine, you can visualize, and of course triangles are visualized everywhere. Even I gave you some examples in my previous video. So however big the triangle is, the opposite by hypotenuse would be a constant. And so the mathematicians decided to give a name to this constant, some name to this constant. And since the opposite side is with reference to this 30 degrees, so we'll have to include that 30 degrees in the name, and the name given to this ratio, opposite by hypotenuse, is sine 30 degrees. So sine 30 degrees is defined as opposite by hypotenuse, right? So sine is just a name given. But when you say sine, you will have to mention the degree along with it, because the sides are with respect to this degree which is mentioned. Suppose I draw a right angle triangle of say 45 degrees. Let me just draw one here. It's not the same triangle. It's say maybe 45 degree each. This is 90 degree, and this is also 45, this is also 45, because they add up to 90 degrees, isn't it? So sine 45 would be a different ratio. The sine 45 would be a different ratio because the opposite here would be different. These two will not be equal. These two will not be equal, but sine 30 will always be the same throughout. And if you compare triangles of 45 degrees, right triangles of 45 degrees, however big they are, whatever huge in size they will all be similar. So all of them would be equal to some other ratio, but they will all be equal to opposite by hypotenuse. So sine is nothing but a name given to this ratio, and we always write the angle along with the name because it depends on the angle. If the angle changes, the ratio changes. I hope you followed this video, and we will talk about there are of course many ratios in a right angle triangle. It is not only opposite by hypotenuse. You can write ratios of other sides also, isn't it? So we have many more ratios, and every ratio has a name given to it, and we will look at all these names in our next video. Thank you.